For the past 2 decades, the tech industry operated under a comforting illusion that the internet was weightless. We visualized the digital world as a clean, ethereal cloud floating effortlessly above our physical infrastructure. But the explosive artificial intelligence boom has violently reintroduced Silicon Valley to the unyielding laws of physics. As we move through 2026, we are realizing that intelligence requires an astronomical amount of raw physical power. The absolute biggest threat to the future of AI isn't smarter code, missing datasets, or government regulations. The ultimate constraint that could halt the entire Silicon Revolution right in its tracks is a severe global energy bottleneck. Every time you type a prompt into an advanced generative model, you are triggering a massive chain reaction of electricity. A single complex AI reasoning query consumes nearly 10 times the electricity of a traditional, classic Google search. When scaled across billions of users, the computational load shifts from a minor digital hum to a screaming energy crisis. Like and subscribe to the channel visual link if you want to master the hidden tech forces shaping our modern world. To understand why AI is so intensely power-hungry, you have to look inside a next-generation hyperscale data center. Traditional data centers were built to store static information like your old photos, emails, and website databases. They required steady, predictable streams of power to keep servers idling and web pages loading on demand. But training a frontier AI model requires thousands of specialized graphics processing units, or GPUs, packed closely together. These elite chips run at maximum capacity, churning through quadrillions of mathematical calculations every single second for months. This relentless crunching of parameters draws an immense amount of electric current, turning data centers into industrial-scale power hogs. A standard server rack historically drew around 5 kilowatts of power, but modern AI server racks demand up to 100 kilowatts. This concentrated energy density creates another massive engineering challenge, which is the generation of extreme, destructive heat. Nearly 40% of the total electricity piped into an AI data center doesn't even go toward computing. It is consumed entirely by massive cooling systems, fans, and liquid chillers tasked with keeping the silicon from melting down. If you are fascinated by the hidden infrastructure realities behind the artificial intelligence boom, make sure to hit that like button. To make things worse, if a data center loses cooling for even a few seconds, the entire array of chips faces permanent thermal destruction. The International Energy Agency projects that global data center electricity consumption could approach 1,000 terawatt-hours very soon. To put that staggering number into perspective, that is roughly equal to the entire electricity grid of Japan. If the global network of data centers were a sovereign nation, it would rank as the 5th largest energy consumer on Earth. In the United States alone, data center energy draw is expected to skyrocket to 12% of the nation's total grid by 2028. This sudden, unprecedented spike in electricity demand is happening at the worst possible time for our aging power grids. Most national grids were designed decades ago for a world where energy demand grew slowly and predictably over generations. Now, grid operators are facing massive connection queues, with some data centers waiting up to 7 years just to plug into the grid. In tech hubs like Northern Virginia, Dublin, and Frankfurt, AI infrastructure is aggressively gobbling up all available local power capacity. This immense strain is driving up utility prices for regular citizens, fueling an expensive cost consumers simply cannot escape. Don't forget to subscribe to Visual Link and turn on notifications so you never miss our weekly breakdowns of critical technology. To solve this emergency, tech giants are abandoning their absolute reliance on traditional wind and solar power grids. While solar panels and wind turbines are fantastic for sustainability, they suffer from a fatal flaw for computing: intermittency. AI training models run 24 hours a day and cannot simply pause because the wind stopped blowing or clouds blocked the sun. They require an unyielding, rock-solid supply of electricity known as baseload power to keep the neural networks humming perfectly. This urgent need for continuous, carbon-free energy has triggered an unprecedented trillion-dollar rush toward a controversial savior: nuclear energy. In a series of historic deals, major tech hyperscalers are investing billions to lock down dedicated nuclear electricity. Microsoft made waves by backing a multi-million-dollar plan to resurrect a closed reactor at the infamous 3 Mile Island facility. Simultaneously, Amazon purchased a massive data center campus connected directly to a 600-megawatt nuclear plant in Pennsylvania. The ambition has expanded further, with tech boards signing massive agreements to fund the development of small modular reactors, or SMRs. These smaller, factory-built nuclear reactors can theoretically be deployed directly next to data centers, bypassing the public grid entirely. Yet, building new nuclear infrastructure takes nearly a decade, creating a massive timeline gap that cannot be easily bridged. To keep their AI models evolving right now, tech companies are being forced to rely heavily on natural gas turbines. This desperate pivot is causing corporate greenhouse gas emissions to spike significantly, threatening to completely derail global climate goals. The tech industry's race to build the ultimate digital mind has created a fierce paradox for our planet's environment. We are building artificial intelligence to help us solve climate change, yet the tool itself is burning through resources at a terrifying rate. Engineers are scrambling to design more efficient AI hardware, like neuromorphic chips that mimic the ultra-low power consumption of the human brain. Your biological brain can perform complex reasoning tasks while consuming a meager 20 watts of power, less than a dim light bulb. Meanwhile, a silicon neural network requires millions of watts, massive cooling infrastructures, and dedicated power plants to achieve similar results. This massive disparity highlights how inefficient our current silicon-based approach to machine learning truly is on a macro scale. Until we can achieve that level of biological efficiency, the silicon gold rush will remain completely bound by the laws of energy. The future of artificial intelligence will not be decided by who has the best algorithms or the most elegant user interfaces. It will be decided by who can secure the copper, the cooling water, the nuclear reactors, and the raw electric current. We are moving toward an era where computing power will be tightly rationed based on local grid stability and resource availability. Tech companies that fail to lock down long-term energy contracts will find themselves completely unable to train their next-generation models. This means the AI landscape could soon be monopolized not by the smartest coders, but by the companies with the deepest energy pockets. As you look out across the rapidly shifting digital landscape, remember that every piece of software has a physical footprint. True innovation requires us to engineer solutions that respect our physical limits rather than pretending they do not exist. Claim your understanding of these invisible systems. Look beneath the glossy interface of tech and respect the material reality of progress. The virtual world is fundamentally anchored to the Earth, and its expansion depends on our ability to power it responsibly. Every byte of data generated by an AI model leaves an indelible mark on the physical infrastructure of our planet. We cannot afford to treat the digital realm as a consequence-free zone while our physical grids groan under the weight of computation. The balance between technological advancement and environmental preservation is the defining challenge of our generation. As we push deeper into this new frontier, the transparency of tech companies regarding their carbon footprints will become absolutely critical. Consumers will increasingly demand to know the exact ecological cost of the digital services they use on a daily basis. This shift in consumer consciousness will force a massive reevaluation of how AI models are designed, trained, and deployed globally. We will see a transition from raw model size to extreme optimization, where efficiency becomes the ultimate competitive advantage. The developers who can create highly capable models using a fraction of the traditional energy will become the new industry leaders. This architectural evolution will mimic the natural efficiency of evolutionary biology, maximizing output while strictly conserving vital input resources. Until that day arrives, we must remain vigilant and aware of the massive physical engines humming behind our smooth glass screens. Keep your eyes on the infrastructure, monitor the shifting tides of global energy, and stay grounded in the mechanics of reality. The road ahead is paved with copper cables and concrete foundations, anchoring our digital dreams to the soil beneath our feet. Never forget that the ultimate limit of human ingenuity is always dictated by the boundaries of our physical environment. By embracing these constraints, we can spark a new wave of truly sustainable innovation that uplifts humanity without draining our world. Stay curious, stay energized, and keep uncovering the massive physical forces driving our digital future. So hit that like and subscribe button for visual link.